Hello everyone, in this video I'm going to explain the concept of maximum likelihood estimation and how it's calculated. The method of maximum likelihood estimation provides a framework for predictive modeling in machine learning where finding model parameters can be framed as an optimization problem. Maximum likelihood estimation involves maximizing the likelihood of a function in order to find the probability distribution and parameters that best explain the observed data. The maximum likelihood estimation could be a bit daunting to follow at first, but I promise you that by the end of this video, you'll be able to understand the notions of maximum likelihood and how to calculate it yourself. I'll be going over different examples of maximum likelihood estimation and how it's calculated using 3 different probability distributions. So hang on with me. As mentioned earlier, the maximum likelihood estimation method estimates the parameter of some model or probability distribution by maximizing something called the likelihood function. Let me first introduce some principles behind MLE. Let's say we have a random variable x and we are given some data or observations from 1 to n. So that's x1 to xn. We are also given some probability distribution or probability mass function defined by some parameter theta, which we believe describes the data or measurement that we have. Now, the maximum likelihood estimation is all about finding the parameters of the distribution. In this case, we are given the data, x, and we need to find the optimal theta that describes this data. This is called finding the likelihood of theta, or L theta. The likelihood of theta is calculated as the joint probability distribution of all observed data points. Here, you have to note that the data points should be independent, but let's save that for another example. To find the optimal theta, we need to find the maximum of L theta. This is done by solving for the derivative with respect to theta at 0. In most cases, however, the derivative of L theta could be difficult to calculate in a standard form above. So we normally calculate the log likelihood. This is because the log has this nice property where log A times B is equal to log A plus log B. This simplifies the equation above to the sum of the logs of the xi's or the observations. You might ask, how can one decide to use the logarithm instead? Isn't this problematic? Well, turns out no, as the natural logarithm is a monotonically increasing function, which means that if the value of some variable x increases, the value of its logarithm log x also increases. This is important because it ensures that the maximum value of the log of the probability occurs at the same point as the original probability function. Okay, enough with the theory. Let's see how this is done through a worked example. Suppose we have observations coming from a binomial distribution, or simply a Bernoulli process, where we flip a coin and look at its outcome. Did it land heads or tails? Let's denote our random variable, or the coin flip, as x. In this example, we have 5 measurements, or trials, with 3 times the coin landing head and 2 times landing tails. Here, the observations are independent, in the sense that the outcome from the first flip does not affect the outcome from the second flip. So, if you tell me that the first outcome is heads or tails, that tells me nothing about the outcome of the second trial. Now let P be the probability of success, or let's say the coin landing heads, and let Q be the probability of failure, or say the coin landing tails. Since the outcomes are mutually exclusive, Q is equal to 1 minus P. So what's the free parameter we're trying to estimate here? We have X, the data, and we're trying to find the parameter P. Alright, now let's calculate the likelihood of the parameter P, and that's equal to the joint probability of observing the outcomes, or the measurements. So that's equal to the probability of X being heads times the probability of X being tails, and so on. Brilliant. So what's our maximum likelihood estimate of P then? LP simplifies to P times 1 minus P times 1 minus P times P times P. Simply when we replace heads by p and tails by 1 minus p. That also simplifies to p cubed times 1 minus p squared. Remember, it's always easier to calculate the log likelihood instead of the likelihood. So the log likelihood of LP, it's log p cubed times 1 minus p squared, which is equal to the sum of the logs, which simplifies to 3 log p plus 2 times log 1 minus p. We need to find the maximum likelihood, so we first need to find the derivative with respect to p. This is equal to 3 times 1 over p plus 2 times 1 over 1 minus p times minus 1 by the chain rule. Alrighty, we need to find the maximum, so we need to set the derivative equal to 0 and solve the equation. So that means that 3 times 1 minus p minus 2p is equal to 0, which says that p is equal to 3 over 5, and voila! We have calculated the optimal parameter p using MLE. Or in other words, we find the optimal parameter p by maximizing the likelihood function in order to find the probability distribution that best explains the observed data. Now, you might have noticed that the average of the observations also happens to be equal to our MLE estimation, which is 3 over 5. If you replace heads with 1 and tails with 0 and average the values, you will get 3 over 5. So, can't we just use the average instead and not bother with all the ugly math above? Well, not really, and I'll discuss this later in this video. Now I'll give 2 other examples of how to calculate the maximum likelihood estimation. But before we move on, I just want to say a word about the difference between the likelihood of the parameter, which is L theta given the data, and the probability of observing the data given the parameter theta. Aren't these the same after all? Well, these expressions turn out to be equal to one another. So what does this mean? Well, remember, the probability of the data given the parameter theta is simply the probability density mass or mass of observing the data with model parameter theta. Now, the likelihood of theta given the data is the likelihood of the parameter theta taking a specific value given that we've observed some data. When you put it this way, it all makes sense. And L theta given the data is equal to the probability of the data given theta. Let's take another example from the Poisson distribution. The Poisson distribution is popular for modeling the number of times an event occurs in an interval of time. Say we have a discrete random variable x, which represents the number of road accidents, say, in Melbourne suburbs on a given day. The probability mass function of the Poisson distribution is equal to the following. It's the lambda to the power k times e to the minus lambda divided by k factorial, where k is the number of occurrences of the event. In our case, it's the number of accidents. As before, we will calculate the maximum likelihood of parameter lambda given the observed data from the joint probability distribution, which is the following. And this simplifies to lambda to the power 23 times e to the minus 6 divided by the product of the factorials. Now, as before, we will calculate the log likelihood because it's easier to derive. And the log likelihood is equal to the 23 log lambda minus 6 lambda minus log of the product of the factorials. When we set the derivative with respect to lambda equal to 0, we end up with a value of lambda equal to 23 over 6. Now, to make sure that it's a maximum and not a minimum, we check the second derivative, which should also be negative, and indeed it's the case. So, the lambda that maximizes the conditional probability of observing the data sample here is equal to 23 over 6. In this example, I will explain how to use maximum likelihood estimation to find the 3 parameters of the normal distribution given some data. But I will give a graphical example to help clarify the intuition behind maximum likelihood estimation. So if you didn't fully understand this from the previous 2 examples, this example will hopefully make things clear. Let's assume we have a sample with the heights of YouTube subscribers. Now, this is an imaginary sample, so of course the numbers are not very realistic. If you remember the probability density function of the normal, there are two parameters that define the shape of the distribution, namely mu and sigma. So this is the probability density of the normal distribution. In this example, we are trying to find mu and sigma that best fit the data by moving and stretching the normal curve to check at which point the curve best fits the observations at hand. So if we move mu, or if we make mu bigger, the mean of the distribution will move to the right side. And if we make sigma larger, then the shape of the distribution will also change and it will get fat the bigger sigma is. Cool, so let's see how this is done. We will calculate the maximum likelihood of observing the data given mu and sigma from the joint probability distribution as before. This is how the joint probability distribution looks like after we replace the values of the xi's using our observations. We will use the log likelihood just as before because it makes life easier. As you can see here, the nasty function at line 2 has been transformed to a sum of the logs of the individual inputs in that function, which is much easier to calculate. I will not go through all the math here to keep this video short, but if you want me to produce a separate video of how to calculate the log, let me know in the comments below. I'll also look at the general example where we have n observations instead of restricting the example to the 5 observations that we have. But don't worry, at the end I will show you how to get the result with the example that we've seen. Alright, let's go through the log likelihood. Each term in the first line will transform into minus 1 over 2 log 2 pi minus log pi minus xi minus mu squared divided by 2 sigma squared. Now this simplifies to minus n over 2 times log 2 pi minus n log pi minus x1 minus mu squared divided by 2 sigma, and so on, where n is the number of observations or number of measurements that we have. We need to find the maximum of the logs, so we need to find the derivative at 0. But in this case, we have two parameters, so this has to be done over 2 steps. The first step is to do the derivative with respect to mu to find the optimal value of mu. The second step is to do the same thing with respect to sigma to find the optimal value of sigma. This is our log likelihood function from the previous slide. Let's calculate the derivative with respect to mu, but again, I will not go through the math step by step, but let me know in the comments if you'd like me to. I'll do it in a separate video. The derivative with respect to mu is as follows. Now, the derivative of the first element is simply 0 because it does not contain mu. The second element as well becomes 0. But the derivative of each of the xi minus mu squared over 2 sigma is negative xi minus mu divided by sigma squared. Notice how the sign changed as the two minuses cancel out. Speeding forward, the derivative with respect to mu is 1 over sigma squared times the sum of the xi's minus n mu. The derivative with respect to sigma is as follows. We are almost there. To calculate the maximum likelihood estimator for mu, we set the derivative with respect to mu of the log likelihood equal to 0. We end up by a value of mu equal to the sum of the xi's divided by n, which is the number of the observations. If we do the same thing for sigma, we find the maximum likelihood estimator or the optimal parameter for sigma, which is equal to the following. Now, let's hold on for a bit and try to remember what we were trying to do in the first place. We were trying to identify the parameters of the distribution that maximize the probability of observing the data. So we were trying to shift the normal distributions along the x-axis and trying to play with the standard deviation to see which distribution best fits the data. Now, if we calculate mu and sigma by replacing the xi's with their values, we end up with the probability density function of the following form. Mu is equal to 3.38 and sigma is equal to 0.495. This is the distribution that best fits our data. So we successfully found the parameters that maximize the likelihood of the model producing the data that was observed. Before we wrap up, let's reflect on that the average of our sample measurements happens to be equal to our maximum likelihood estimation. We didn't know that before calculating MLE, but this shows that our maximum likelihood estimator is an intuitive estimator as it happens to be the same as the average of the data from our sample. It's not always obvious though that the average of the sample is equal to the maximum likelihood estimate. What if the data comes from a gamma distribution? That's all folks, I hope you enjoyed this video. Don't forget to like, share and subscribe.